In this video, we're going to be talking about the disconnections for the Claisen reaction. So in this one, just like with our aldol reaction, we're going to go ahead and label our alpha and beta in our product and do the retrosynthesis. So the alpha beta is based off of the ester group. So carbonyl 1 is going to be the carbonyl carbon. Carbon 2 is going to be the alpha carbon, and carbon 3 is going to be the beta carbon. And again, we're choosing that beta carbon because it does have some functional group on it. So carbon 6 technically is also a beta carbon, but it doesn't have any functional group, so that's not going to really help us for our synthesis. When we take a look at the alpha-beta bond, the first thing we're going to do is disconnect that bond just like we did in our aldol. However, what we're going to do on this other side of the arrow, we're going to end up making the beta carbon have the OR group. In this case, we're going to choose OCH3 because our product had a methyl ester. So we have this methyl ester here. So we're going to choose that same group as our OR group. And so that's why I chose the OCH3 to put on that beta carbon. That beta carbon was carbon 3, and it's still attached to carbons 4 and 5. The other compounds that we're going to do something very similar to what we did with the aldol. We're going to make the alpha carbon into that enolate. So that alpha carbon was carbon 2. Now it's in the form of an enolate. It's still attached to carbon 6. And then the last thing that we're going to do for this one is to transform that enolate into carbonyl, because the first step in the reaction is to make that enolate. And so this last step of our retro is going to be to show what carbonyl that enolate actually came from, which would be this carbonyl here. So let's number our carbons. What we can see when we did this, we have methyl ester with 3 carbons. These two carbonyls that we're going to be combining in our reaction are the same. And so that gives us some idea of how we're going to set up our synthesis. So for this one, our synthesis, we can put in our methyl ester. This is the only carbonyl we have to show because some of it's going to be converted to enolate and then some of it's going to stay as carbonyl and be attacked. For the base that we use, we talked about this base being very important in our Claisen reactions, and we're going to want to make sure that we're using a base that matches the ester. And so we have a methyl ester, so we're going to use NaOCH3 as our base, or sodium methoxide. That's so that if that base goes and attacks at the carbonyl carbon, we're just going to get that same ester back. We're not going to destroy our ester, and we're not going to do some kind of trans-esterification where we get a new ester. And so that's why we're choosing that NaOCH3 as the base. And then our second step, because at the very end of that mechanism, when we make that product, the alpha H that's left on carbon 2 when we originally formed this product in the solution, that alpha H is very acidic. It's going to come off under those very basic conditions. And so our second step, we do have to make sure that we're putting in our H3O plus so we can protonate everything and get our product back. And that's going to give us that product that we've shown. So that's how we would approach the synthesis for Claisen, a self-Claisen reaction. So that's what we had here. For our next molecule, we're going to approach it the same way. So we're going to look at our alpha and beta carbon. We're going to label them based off of the ester. This time our ester is on the left-hand side. And so carbon 2 is going to be our alpha carbon because it's the one beside the ester carbon, which would be carbon 1. And then carbon 3 is our beta. So what we're going to do, we're going to disconnect that alpha-beta bond, and we're going to be adding an OCH3 group to carbon 3, so that OR to the beta. Our alpha carbon is going to be the enolate. So let's just redraw this one as the enolate. And then that beta is going to get that OCH3 group. We want to match those esters. Last thing we're going to have to do in this retrosynthesis is to convert that enolate to carbonyl. So that's going to look like this. What we notice about the two esters that we're starting with, just like when we were comparing the two carbonyls, usually aldehydes for our aldol reaction, we see that those two esters are actually different. And so we have to worry about how we're doing this reaction. We also have alpha H's on both of them. So we have the alpha H's on carbon 2 and the carbonyl at the bottom. Those are the ones we actually want to be taken to make that enolate. We also have alpha H's on carbon 4 on the other carbonyl. So we do have to worry about how we're going to set up this reaction. So we go back to that strategy that we used for our aldol. And in that strategy, we were controlling that order of addition and using an irreversible base. We're going to do the same thing here. We're starting with the carbonyl that we actually want to form the enolate. So that's this one here. We want to make an enolate out of that one. So we're going to put that one on the left-hand side of the arrow. We're going to treat this with an irreversible base, so LDA. This base was very large, so we're not going to have those problems of attack at the carbonyl carbon like we had with something like NaOH, and so this is not going to be able to do that. So we're okay using that base there. Then once all of that ester is converted to the enolate, we're going to add in our other ester that we want to be attacked. So that's going to be our step 2. And then our last step, we do need to make sure that we add in that H3O+, and so that can protonate all of the molecules of the product and give us our final product. So with this one, we approached this very similarly to how we did the aldol disconnections. We just had to add an OR group to the beta instead of just kind of oxidizing up that beta with another bond to the same oxygen. We kind of added a new oxygen in there. And we also had to take a look at the two carbonyls that we got out of this to see, are they different? Are they same? If they're different, we do have to control that order of addition.